Now I want to teach you something that these books of professors trying to learn something while they're giving lectures but not understanding it, it's not covered there, but it's really the essence of the subject. This is the following thing. What's important about chaos is not time evolution, because this argument I just showed you tells you that future is unpredictable because we are losing information about where it came from as a logarithm of the number of steps we look in the past times the rate, this Lyapunov exponent. And we cannot beat that because exponentials will always win out. So weather will always be unpredictable. So the job of the weatherman is not to say what the weather will be like in 3 weeks or 6 months, even though there are some criminal websites that pretend to do this, because that cannot be done. That's mathematically obviously not possible. The job of weatherman is says, what kind of weather are there? So the real essence of chaos is that the weatherman has to tell you there is a 5% likelihood of hurricane of this kind, of tornado of that kind, or a balmy weather of that kind, or, sweltering, unbearable temperature of that kind. I'm supposed to have a repertoire of possible behaviors. That's called geometry of the state space, what are coarsely speaking possible things. And then I have to give you some rules saying that if I see this kind of weather, I have a likelihood of seeing that kind of tornado. That's called a Markov graph or something. But your basic job is really to find what are possible things. And when you think of that, the time, it's very painful for us to give up on time, but time evolution, we are supposed to tell you what kind of things it is. Now, in other branches of physics, we always do this. So we tell you there is an electron. We don't tell you the electron is in Sanjian and, at what time you see it. That's irrelevant information. One possible outcome of expansion electron, it has mass, it has charge, it has spin, etc. So the same thing is true of chaos or turbulence. I'm supposed to tell you, I'm seeing this thing and has a name. And that's where our applied mathematics colleagues and our professors who are tenured, I don't know how long it'll take for them to get it, but it's not working very well. In other words, we have to find all possible outcomes. That's done not by evolving in time, but by other methods. So I'll give you a sense how this works. So far I told you the chaos was created by Bernoulli map. And Bernoulli map was something that I stretched the neighborhood. And then I had to, translate it back into unit interval by this shift, the winding number, or whatever you want to call it. That equation forward in time can be written as one-step difference equation on a lattice. What is the lattice? In this system, the time takes integer values. It's time 1, 2, 3, 4, 5, or -7, -6, -5, etc. So there is an integer lattice. That's all possible values of time. And on this integer lattice, I have a condition on the neighbors. This is the law. It says these two neighbors differ precisely by integer given here. That's called source or alphabet. And this kind of problems are solved globally, meaning if I want to have a lattice of 7 sites, meaning if I want to know all possible things that can happen if I look at a system for 7 days or 7 years or whatever my map is, unit of time is in integer system, Then I have to specify all possible fields, meaning, values of temperature or whatever I'm measuring. In this case, it's called a scalar field, just one-dimensional thing, consistent with my law, which says I have to look at my neighbors and I have to be nice, play nice, so I have to look at what they're doing. And the marching orders, which are these guys here, which says, how far I'm allowed to jump. I'm not sure this picture will help very much, but basically the idea in Bernoulli is that, there is a temporal lattice in time. At each time, I can be in one of the, let's say, 4 possible subintervals. And then one step in time, I can jump into some, but not in the others. That's called the law. And I have to figure out all possible trajectories consistent with this law. I call it Bernoullistan. If you don't understand the picture, don't worry about it, doesn't matter. So the idea is that in chaos, you cannot predict future. You have to enumerate all possible futures, and then we can discuss which one is more or less likely to do. And the way you do this is you have to think globally. That's called climate rather than the weather. But you have to act locally. You have to find kinds of weather which is consistent with the outcome, which is called climate, a long global term, one possible example of weather after some time. So you have a local condition, and you have an equation. Whenever you have a finite set of latticite, you can think of these guys as a vector. You can think of the fields as a vector and things. And this law says, when I look at the teeth component of the vector, I have to compare it to the neighbor and multiply it by s. So law of evolution is, in this case, it's a linear case, it's some kind of matrix. And now I have to find all possible solutions of this. Now, how you do this? In this case, it looks trivial, but it turns out it carries to much more serious cases. So it says, I have my state of the system. And now, when I multiply it by this matrix, but in general, it'd be nonlinear function, it has to agree with the order I've been given. This is this M. And this thing in general, if I had a nonlinear function, would be a linear approximation to the neighborhood of phi. So it's called Hill matrix. It comes to us from late 19th century from a gentleman astronomer who gave up on teaching in Yale because he hated the undergraduates at Yale and, was rich enough just to live in his house and do astronomy. You now have to enumerate all possible solutions. And you are now in a large dimensional state space because the field at each point is some number between 0 and 1 in this particular example. And a solution consistent with equations of motion is actually a point in the space. You go to high dimensional space, which is all possible kinds of weather, discretized to 7 steps forward. And instead of trying to advance forward in time and losing control because it's exponentially impossible to do this, you simply solve this kind of matrix equation and find fixed points, and that's what it is. So that's a modern way of thinking of chaos. We enumerate all possible kinds of weather without stepping forward in time, because that's impossible. We cannot actually advance system because no matter how we do it, after a few steps, we lose all the information about it. And, that's why the weather at best is predictable 5 days in future. But a good, weather person will tell you what kinds of weather there could be in Chicago or in Atlanta. And now there's a bit of beautiful mathematics. You ask yourself what this matrix is, and in this case, you can actually visualize it. My colleagues call this fundamental fact. So what this matrix says is if I have a field, I multiply it by a matrix, which means I had a vector and I, stretch it out in some other vector. If vector is in a hypercube, when I multiply hypercube by the matrix, I get some kind of parallelepiped. It's called fundamental parallelepiped. In that fundamental parallelepiped, if I add a sequence of integers, this M is my marching orders. There's some integers being first, seventh, fourth interval. I get to 0, and when you look at this geometrically, you can actually see what it does. So if you start with a unit, for period 2, you're looking at 2-dimensional space. So you have a unit square, hypercube is 3-dimensional. When you multiply it by this matrix, you get a parallelepiped. That parallelepiped has 3 times the area of the original thing. And that volume turns out to be number of periodic points. So there's a very cute interpretation of what these things are and how you solve them. In 3-dimension, a cube, becomes a hypercube, and its volume again can be understood to be the number of periodic solutions or the periodic solutions. There are things like this. There are things on diagonal. For example, these are fixed points. But, and here was a period 2. This is a periodic solution of period 2 for this system. There is a way of using linearized neighborhood of your orbit to count how many there are. And there is an amazing formula from 19th century discovered by astronomer Hill and proved by Poincaré that relates this volume to the volume of integration in time, which is too advanced for this. But for modern people, chaos is not evolution in time. It's just that Hill determinant has a expansion, meaning if I use a unit cube, the volume of Hill determinant, which is what happens when you multiply unit cube by this stretching, local stretching, that has to be larger than 1. So that generalizes the notion of Lyapunov going forward in time. But now without thinking of time, you're just counting invariant solutions consistent with laws that you're studying. And then the number of field configuration is the number of fixed points in the problem, periodic solutions on a lattice. And that's a modern way of saying that a system is chaotic. And it's set up in a way that quantum field theorists think about field theory. They think about space-time as space-time, and on it there are configurations called fields. For example, wave function of a meson, or multi-component field called spinor that describes an electron or something. When you do this, you don't move forward in time. That would be very stupid when you have special relativity where space and time are related by Minkowski invariance. You actually just investigate all possible solutions consistent with this. And that's it. Now you know it if you didn't know it. But the rest is a little bit too advanced for our course. But the main thing is that once you know how to count these periodic points, then you have to ask yourself, what is it that you're trying to do? And of course, there is no reason why I should predict weather 7 days in advance. I might want to count possible kinds of weather 8 days or 3 days. None of these individual numbers are meaningful. What's meaningful is description of all possibilities, which means weathers of all, predictions of all length. That in statistical mechanics, field theory, etc., is a counting problem, and it's solved by defining generating functions. So these are functions that have coefficients. So in this particular example, the natural function is to look at exponential all your possible counts, because when you had a periodic orbit of length n, there were n periodic points, but they were all the same. So to count just different orbits, you have to divide them by their length, and that's a natural way to do this. And when you're very clever with this, you describe all possible outcomes in terms of all possible periodic points in a smart way, and you get some amazing results. For example, when you do this for Bernoulli, it turns out that if you look at a rational function, which in this case happens to be linear in Z of this form, you actually know how to enumerate all possible solutions. So this is periodic orbit theory, and if you don't know, now you know. Now there are some dotted things to be included in this theory. Basically, for your purposes, is you have to think of this. Whenever you have chaos, it cannot be predicted. Newtonian way of just stepping little steps in time is a delusion, because all such steps end up in exponential explosion, and you cannot beat exponential. So forget it. That's not the way how to think about unstable problems, which are where the numbers of solutions grows exponentially and errors grow exponentially. It cannot be done. Not all hope is lost, because what you understand is you don't have to describe any particular trajectory in space-time. You have to enumerate. It's like a book of life. You enumerate all possible lives, all possible trajectories that are allowed by the law. Now, law is very strict, so you can't do crazy stuff. Laws only allow very few things compared to, some crazy thing. So if you have a cup of coffee with cream in it, you can try to explode it like a supernova, but that's not going to happen. Any motion will be very simple, and there'll be very few possible patterns you will see in that viscous fluid. So the laws are very constraining. I mean, out of all this world, you have to enumerate those things. Each one of them is a fixed point condition in this space of possible states, meaning there is only one way I can arrange past and future to get this particular solution. But their number grows, so I have to count the number. And if I'm good in counting them, I should give you a zeta function, which is a very compact generating function that generates all possible answers. And if you do this, you're a modern professor and you can go home. You have solved a problem. Now, in statistical mechanics, this is called partition function, and examples of the Ising models and solving this means you solve for all possible states of an Ising model. In quantum field theory, this is called a path integral, and you solve for all possible combinations of protons, neutrons, quarks, or whatever the theory is supposed to describe. And in deterministic chaos is you again count how many possible solutions to this are. And determinism is both easier than quantum mechanics because everybody understands what a fixed point of Bernoulli map is. There is nothing to think about. It's abstract. It turns out to be harder than quantum mechanics because quantum mechanics stops at h-bar scale, so you don't have to resolve things finer. But as we'll see, when you start fractals in determinism, you're allowed to blow up details infinitely many times, and that makes it a very hard problem. Now, in stochastic mechanics, which is what you need to know if you work for a hedge fund, you're in much easier situation because you don't care about numbers smaller than, let's say, 1 cent or fraction of cent. So you have some natural cutoff, and these problems become doable again. You can enumerate outcomes and make good predictions. So it turns out determinism is somehow the easiest to think about and actually the hardest to control mathematically. So there are, for example, very few systems other than Bernoulli and Lorentz system that we know are purely chaotic. There are almost no other system mathematically we can prove are ergodic, meaning they don't have stable things. Everybody's mixing and unstable. Okay, this was my spiel for modernity. Next time, how my friend discovered a revolutionary way of thinking about chaos, which shaped much of the last 19th century and is maybe not so important today, but it's conceptually very important for development of this subject.